Chapter 7 is about confidence intervals. And I made this section absolutely enormous in terms of how long the notes are. And that's because this is actually a really hard thing. The computation, I think you can argue, isn't. Even if you were going to do it by hand, yes, you do end up having to simplify a relatively complicated square root. But once you know how to do it, you could do it over and over again. And on top of that, you could actually do all the computation in StatCrunch and just get around all the algebra anyway. So going from having the raw data to getting the confidence interval, that's actually not that bad. The thing that I think is hard is knowing what the confidence interval represents. So knowing how to interpret it. That's the tough part, and most of the extra stuff that I added in, it's really about that. It's not about the computation. So this is long, but that's why it's there, because I think that part is hard. It's really subtle, and that's one of those things where if and I did this too initially. Like when I first encountered this stuff, I was still thinking of it like it was a math course. And if you think about it like it's a math course, that makes the ambiguous parts, like the interpretation, harder. So I guess it's because of that I ended up adding in all that stuff. But anyway, to start going through this, we've already talked about the idea of a point estimate a little bit. It shows up in chapter 6 where you have things like x bar is a point estimate for mu, or p hat's a point estimate for p, right? Like those are the best estimates that you can use. But the thing that would be better than a point estimate would be something called an interval estimate. So the interval estimate, that's going to be the confidence intervals. So I guess I can kind of abbreviate it like that. But that's what we're going to end up doing. And the interval estimate is better because if you just have the point estimate, then there's a part that's left completely undefined. Because you think, well, if you get a point estimate, you don't expect it to match up perfectly, right? You wouldn't expect p hat to exactly match p, or x bar to exactly match mu. You'd say, well, it's probably close to that, right? That's what you'd expect, that it would be close. Okay, what's close, right? Like how close do you have to be, right? If it's a proportion, is within 0.02 close? Is within 0.04 close, right? Like what's close enough? So with a confidence interval, we can sort of quantify that idea. So in this example down here about wearing business attire, so there's our point estimate right there, that 9%. You'd want to convert that into proportion form, so okay, 0.09. And you could make that prediction of just the point estimate of saying, well, we'd expect exactly 9%, but that's very, very unlikely to be correct, that it would match up exactly. But thinking, well, it's probably going to be close to that, that seems reasonable. But then here's the big question. What is close, right? Is close going to be, well, we got a point estimate of 9, so we're thinking it's probably between 7 and 11? Or are we thinking it's probably between, 5 and 13? Something like that, right? What does close actually signify? There are a couple things that factor in, and they're in bold: sample size, confidence level. Because with the sample size, if you have a bigger sample, you have less sampling variability. So then the size of your sample factors into what would be considered close. And then the confidence level, because you can have different levels of confidence. They're all fairly high. Because if you think in terms of percents, like between 0 and 100%, you'd want to be more confident than less confident, right? You can't be 100% confident, because then you would need an interval that captured all possible values. I guess for a proportion you could make one, but it would be kind of useless, right? It wouldn't be very interesting. But you want to get it to be kind of high. So with our confidence levels, we're going to be at 90% and up. We'll have 90%, 95, which is actually the most common, and then 99. So what's a confidence interval? It's an interval that you can compute based on sample data, and it uses a method that would capture the actual population parameter for a specified proportion of all samples. And that specified proportion part, that success rate, that's your confidence level. So 95% confidence interval, going to capture the parameter in 95% of all possible samples. A 90% confidence interval, going to capture the parameter 90% of all possible samples. The thing that's going to be sort of cryptic, I suppose, would be that in reality, we're only going to have one sample. We're not going to have all possible samples. So we're never going to know for sure if our one confidence interval is capturing the parameter or not, because we're not going to know what the parameter is, right? So maybe it does, maybe it doesn't, but our confidence level, that'll, make us feel a little bit more comfortable if we have a nice high confidence level, where we say, well, in this method, 99% of all possible samples are going to capture the parameter, and every once in a while, 1% don't. And we'll never know if our one sample is giving us one of the 99% or one of the 1%, but if we're 99% confident, then it seems like it's pretty likely that we're going to end up capturing the parameter. Okay, so how do we figure out a confidence interval? Well, in general, you do use the point estimate. So what it ends up being is it's the point estimate, and this is where you'd have your x bar and your p hat. Those are point estimates. Plus or minus the critical value, whatever that is, times the standard error. Okay, so what does this mean? Well, I guess I can diagram this in a different color. So your point estimate, so this ends up being things like p hat or x bar, right? Where we said that p hat's a good point estimate of p and x bar is a good point estimate of mu. So like the sample-based version of whatever measure you're interested in. You're interested in the population mean, you're going to use the sample mean as your point estimate. Interested in the population proportion, you're going to use sample proportion. The critical value, this here is determined by the confidence level. So we'll get there. And then the standard error, we've had this show up before. This is just the standard deviation of the sampling distribution, which is a thing from chapter 6, right? And depending on if you're trying to estimate a proportion or trying to estimate a mean, these are going to look a little bit different, right? The standard error for a proportion, the standard error of the mean, they don't look exactly the same. They serve the same function, but the formulas look a little bit different. The other way of writing this, or point estimate plus or minus the margin of error. So really what this is saying is that, and I guess I can put this in another color. How about brown? So I'll just put this down toward the bottom parentheses, that the margin of error is just a term for everything that comes after the plus minus. So it would be the critical value times the standard error. And there is an easy mistake to make, and you know what it is before I even say it. It's considering how similar these terms are, margin of error and standard error, the common mistake is thinking that the margin of error and the standard error are the same thing. And that's almost right, but not quite, because the margin of error is a standard error multiplied by the critical value, right? So they're related to each other, but they're not exactly the same thing. And our book uses the term margin of error a lot, but that's all it means. It's just the stuff after the plus minus. So critical value times standard error. And so as before, standard error is the standard deviation of the sampling distribution. And so the three things that you would need to compute a confidence interval, at least for a proportion, are going to be these three, right? Because the sample proportion, that's your point estimate. So I guess I can put that in here, right? Like that's going to be your point estimate, but it also shows up in the computation of the standard error. So that's a really big thing. You need the sample size, So this is, I'm going to say in the standard error. Sample size, this is also in the standard error. And then the confidence level, you need that for the critical value, which I'm just going to abbreviate as CV for critical value. But that's where it factors in. The confidence level is going to give you that piece. All right. So then there are some conditions for inference that need to get satisfied. You want individuals to be independent of each other. If you have a random sample, you're good. Ideally, a simple random sample, right? Like the theory is based on like the easiest situation that we had that was a good sampling method. But really, if you have a random sample in general, you're fine. But that's not really a thing we're going to be too concerned with. The probability of success should stay the same from one trial to another, just like with a binomial. This also typically isn't a thing that we're going to have to check. The thing that we might have to check once in a great while is this, that the number of successes and failures should both be at least 5. So sometimes this is phrased as at least 5, sometimes it's phrased as at least 10. So here our book is using the at least 5, so we'll go with it. That shouldn't be a problem. The only time where that might cause trouble, I guess, would either be if your sample size is really small. You know, like if your sample size is 12, you probably got to check, right? But the other way is if your sample proportion is really extreme. And by really extreme, I mean either like really close to 0 or really close to 1. Because if it's like you've got a sample of size 1500, but your sample proportion of successes is like 0.998, like that's really close to 1, you better check and make sure you got at least 5 failures, right? So that's the kind of thing that, I mean, I don't really think that's going to crop up, but that's where it might fail in the situation where it's not a tiny sample. So usually if you got to check this last thing, it's just if you got a tiny sample. Next, the critical value, where does that come from? Well, we know that it's somehow related to the confidence level, right? That if you have a different confidence level, you're going to have a different critical value. Yes, that is true. Basically what happens is if you have a big enough sample size, then you can apply the central limit theorem and you can say, well, then the sampling distribution is approximately normal, and then you go from there. So the critical value does depend on the confidence level, but also it depends on what kind of parameter you're estimating. Because if you're estimating a proportion, you can just use a standard normal to get the critical value. And we know what that is, right? The standard normal, that's a normal distribution with mean 0 and standard deviation 1, right? So we know what that is. Our book uses this notation with the subscripted alpha over 2. I just use Z star. I think that makes it stick out enough, and I don't like writing the alpha over 2 over and over. Admittedly, that's kind of what it is. But also, like when I learned it, we used 2 books, and one used the alpha over 2 and one used the star. So it seemed like it was pretty arbitrary, and I thought, well, hey, I'll just pick one, and writing the star is a little bit faster. So I think that was about as hard as I thought about it at the time. So now that's my reflexive go-to, so to speak. But when you estimate a mean, even though you use the central limit theorem the same way, because you don't know the population standard deviation, and we'll talk about this more in section 7.2, you have to use something called student's t-distribution. It's like a standard normal, but more adjustable, like more adjustable in the thickness of the tails. We'll see it when we get to 7.2. We're not really going to need it in this section, but this will happen. You do have to use a different distribution here. This section's about proportions, so we're going to stick with the standard normal for now. So we're going to do things like this. So the way you can get a critical value, you can figure it out as the positive. It doesn't have to be the positive bound, because the way that the confidence interval formula is set up, if I scroll back up for a second, notice how it's got a plus or minus. If you just use the negative bound instead of the positive bound, it's not going to matter because of that plus or minus. You'd actually get the exact same answer. So where it says positive right here in parentheses, The only reason you use the positive is because it makes the algebra slightly easier, right? It's a little bit easier with a positive number than a negative number. That's all that that's about. But basically what you do is you take your reference distribution, which here we've got a standard normal, right? So I guess I can put that in here, that this is standard normal. And the software that I use to make this thing is called StatKey. And we're actually going to use StatKey a little bit in a second to fill out the table that's underneath. But it's standard normal because it says it's a normal distribution, mean is 0, standard deviation of 1, right? But then you look over here, and to get a 95% confidence interval, we'd need its critical value. So what you do, and it actually says it up next to the bullet point here, you want the probability in the middle, or the area in the middle, to match up with a confidence level. Look at that thing, 0.95, that matches up with 95%, right? So that's what I did. I said, I want a 0.95 in the middle, and then the cutoff right here, that is the critical value. The way that our book talks about this is it talks about what's left over in the tail. So yeah, I mean, if you have 0.95 in the middle, you're going to have 0.05 left over in the two tails combined. But because this is a symmetric shape, then half of that leftover 0.05 is going to be in each tail. So you get a 0.025 on the left and a 0.025 on the right. Sure, I think it's easier to understand by matching up the middle because that's the same number as the confidence level, right? You go 95% confidence, I need a 0.95 in the middle. 99% confidence, I need a 0.99 in the middle, right? That kind of thing. All right, so the common critical value table. So the alpha over 2, this is the tail, right? And then, so yeah, there's the 0.025 up there in the tail. You can still see it there on the screen. And the critical value, it's that cutoff. So 1.960 or just 1.96. And I think of it as the cutoff for that middle region that the area is going to match up with the confidence level. So how do we get these other ones? Well, you won't need to actually derive these in the future, but I can show you where they come from. I certainly don't think it hurts. So this StatKey thing, this is free. You don't need to log into it or anything. If you Google StatKey, like if you really want to look at this thing a little bit more, you can do it. Most of it is for simulation, which we're not actually going to do, like bootstrap and randomization. Like it's in our book, but we're not actually going to cover it. The things that we need are down here, where it says theoretical distributions, normal, and t. Right now we want normal, so I'm going to click on that. And then I'm going to get a thing that should look an awful lot like the picture that's there in the notes. And notice the default is the standard normal. Got the mean is 0, standard deviation of 1. And then over here in the upper left where I have left tail, two tail, right tail, I'm going to select two tail because that allows me to specify what goes in the middle. And now this thing looks exactly like the picture in the notes. But the next confidence level was 90%. So I'm going to change this. I'm going to click on this button, and I'm going to change the proportion in the middle to 0.90, so it matches up with 90%, right? Because now I got the 0.90 in the middle, and then here's my cutoff down here of 1.645, and then notice what's in the tail changes too, because if you got 0.90 in the middle, you got 0.10 left over in the two tails combined, so half of that in each tail, which is 0.05. All right, so going back to the notes, we had a 0.05 in the tail, and the critical value is 1.645. So if I just go back to it for a second, there you can see it right there as the cutoff for that central region. Then for 99%, I just have to go and change the middle again, this time to 0.99. So with the 0.99 in the middle, the cutoff is 2.576, and if you got 0.99 in the middle, you got 0.01 left over. So half of that, which is 0.005, is in each tail. All right, so the 0.005 in each tail, but the important thing is the critical value, which is 2.576. All right, that takes care of that page. All right, next thing, this is basically how confidence intervals work. So if you have a big enough n to apply the central limit theorem, then you could say the sampling distribution of p hat is approximately normal. And you could approximate it by normal distribution of the mean of p and standard deviation of that root. That's from back in chapter 6 when this came up. I think it's 6.3 or 6.4. that this is in. I'm leaning towards 6.4, but it's in one of those. So then 95% of the sample proportions should be within 1.96 standard deviations either way, right? So I'm using the 1.96 because that's what I just got, from the normal distribution, from the standard normal. So here I'm using that like it's a critical value, right? I've got it in that spot. So I'm saying, okay, if you go 1.96 standard deviations either way, that should be exactly 95% of all sample proportions. At least if, I guess, if we're taking the approximated shape as an absolute truth. Then that would mean that for a single sample proportion, then the probability that it's in between p minus 1.96 and p plus 1.96 is 0.95. So there would be a probability of 0.95 that p hat would be in the interval from whatever this number is up to whatever this number is. However, you can't actually figure out these numbers because you don't know what p is, right? So this is true in theory, but we'll never be able to actually get this interval. So what we do is we construct the interval based on our 1p hat, right? So this is, I guess, the big theory part here, right? We've got to use p hat, and that's all we know, right? We don't know what p is, so we've got to make a couple of adjustments. So first of all, in order to actually be able to compute that square root up there, then what we're going to do is sub in p hats as point estimates for those p's, because we'll actually have a number for p hat, so we'd be able to compute this thing over here, right? We'd actually be able to get a number for this. And also, because you wouldn't know what p is, you would use p hat to figure out if you have a big enough n to apply the central limit theorem. So really that means that you'd be figuring out n times p hat and n times 1 minus p hat, I guess just like it says right down below. So then the way that you would compute the confidence interval, it's going to look like this. You're going to have your point estimate of p hat, then plus or minus your critical value, which our book would use this notation, z sub alpha over 2, and then times the square root of p hat times 1 minus p hat over n. So that whole thing underneath the radical. Or if you want to write it the way that I write it, p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. And I guess, or occasionally p hat plus or minus e, where that's the margin of error, because that sort of thing actually shows up in the homework, which is why I'm bringing it up now. So the e, that is the margin of error, right? But then if you look at these, right, it's like basically, right, like there's your point estimate. Then the z star, or I guess back on the left, the z sub alpha over 2, that's your critical value. And then the whole root, that's the standard error, right? So it's that same formula that showed up before written in words. It's just now for proportions, we can be a little bit more specific and we can use the symbolic notation to make this a little shorter. And so then I guess I kind of got everything labeled here. But yeah, that's the idea. If you've got a big enough sample size, then this is how you would do it if you were going to do it all by hand. So let's see. We have that example about wearing a suit to work, or I guess wearing formal business attire to work. It doesn't have to specifically be a suit. So in a Gallup survey of 547 employed adults in the U.S., 9% said they wear formal business attire to work on most days. All right, so we need three things to get the confidence interval. We need sample proportion, which we have. It's 0.09, right? It's the 9%, right? Like this is where p hat's going to come from. You just have to convert it into decimal form. Then we need n, but here's n, the sample size, right? So p hat's 0.09, n is 547. And then the other thing is right there, that 95% confidence level. So the other thing is that with 95% confidence, that would mean that Z star, or if you would rather, Z with a subscript of 0.025, whatever notation you want to use there, either way it's 1.96, right? We already figured that one out, and it's always 1.96. You don't have to keep deriving that every time. There's never going to be a surprise. So okay, let's do it. So we would have p hat plus or minus Z star times the square root of p hat times 1 minus p hat over n. It's not the best looking hat. There, a little better. Okay, sub everything in at once. That's what I would say. You might as well. It's easier like that. So p hat is 0.09, then plus or minus the critical value, which is 1.96, times, and then underneath the radical, p hat is 0.09, but then 1 minus p hat would have to be 0.91, right? That's what 1 minus 0.09 is. And then you divide by n, which is 547. If you're going to use your calculator to do this, what I would suggest is that you do the entire margin of error all at once. So I'm assuming like if you're not going to use StatCrunch to do it. What I would suggest is if you have a TI, which I should have somewhere behind me. Let me check. No, I don't know where one is, but I actually know this off the top of my head anyway. If you have a TI, like one in the 80s range, then the function that you're probably going to want is the ANS function, which is going to be the secondary function of the sign key. Sign like SIGN, like plus minus, not sign like trig. The inverse function of that one is the inverse sine function. But it's down toward the lower right. It's like right next to the enter key. It looks like a minus sign with parentheses around it. There should be an ANS on the body of the calculator right above that button. So that's the secondary function. So it's second key and then that'll give you the previous answer, because the easiest way to do it, I think, if you're going to do this with a calculator, is do the thing under the radical first, then take the square root of ANS and then multiply by 1.96. That's what I would suggest. So if you're going to do this with a calculator, I would suggest knowing where ANS is, or recall, depending on what model calculator you have. I think maybe Casio's call it recall, which if you see an RCL, that's recall, because sometimes it gets abbreviated. But anyway, if you simplify the whole margin of error using the calculator, you'd end up with 0.09 plus or minus. And if I round this off to 4 places, you get 0.0240. And then to get the endpoints, I guess I don't really need that 0 on the end, you'd end up with 0.066 to 0.114, right? Because the 0.66, I guess I can kind of do this off to the side, the 0.09 minus 0.024 is 0.066, right? And then the 0.09 plus 0.024 is 0.114. I will say one other thing. If you're going to do the confidence intervals manually, watch out for the lower endpoint, because it's possible to subtract in the wrong order. So just make sure you don't do that. Make sure it's point estimate minus margin of error rather than the other way around. If you flip the order, you'll get the negative of what you're supposed to get. And if you're getting a confidence interval for a proportion and you're getting a negative endpoint, that's probably wrong, right? Because that would be something that happens less than never, which doesn't really make a ton of sense. So probably not going to be right if you're getting a negative endpoint. So how do you do this in StatCrunch? If you would rather do it that way instead of using your calculator. And this is way faster, by the way. And it's totally fine to use StatCrunch to do these rather than grinding it out. But you would go to Stat, then Proportion Stats, one sample with summary. And then there's this other stuff here. I'll just show you. I think that's easier. What you would do in StatCrunch is you go to Stat, then where it says Proportion Stats, you go there. then one sample because it's just for a single proportion. And then if you go to with summary, then where it asks for the successes and the observations, the number of successes would be your, it's your numerator, although that's assuming that you've got your proportion written out as a fraction, which we didn't have, right? Because we just had 9% of 547. But you would put it here, and so like for us, we'd put the 547 there, right? And then we don't have the number of successes, but if we did, we'd put it up there. Then down here, and let's say, you could probably cheat with this a little. Let's see, so this little calculator can handle this. So 0.09 times 547, about 49 should do it. So let's say if we put a 49 in there. And then you want confidence interval. Hypothesis testing is what we're going to do in chapter 8, so we're not going to worry about that right now. And we want a 95% confidence level, but if you want a different one, this is how you can change it. And then the method you can just leave is standard walled. That one, I think, is certainly one that would be less common, the Agresti cool. So stick with standard walled, compute. Oh, look. If you round that to 3 places, 0.066, 0.114. That's what we had, right? Like if I go back here, 0.066, 0.114. The reason that the margin of error is slightly different is because in the computation that we did here that I have all written in blue, the sample proportion's rounded off, right? It's rounded off to 0.09. And it's not rounded off if you actually had the numerator. So that'll cause a slight computational difference. But the steps are right here for how to do it. So I guess this is the drop-down menu part, steps 1 through 4. And then successes and observations, basically it's numerator and denominator in that order. And that'll basically do it. All right, so then this one down here, the proportion of passengers that bring only carry-on luggage onto a flight. So in a random sample of 200 passengers, 44 have only carry-on luggage. Notice here, right, there's our sample size, right, there's n, the 200. But then there's the numerator, right? So that 44, that's going to end up being the number of successes. So this time we actually have it. All right, well, we're going to need the same stuff. And oh, look, 99% confidence interval, not 95. So we're going to have a different critical value. So what we've got so far, like if we were going to do this by hand, which I guess we can do that first, and then I'll run through it in StatCrunch. The sample proportion, it's 44 out of 200 that just had carry-on luggage. So that's how you would make the fractions. So 44 divided by 200, which works out to be exactly 0.22. N is 200, right? We need that, but we kind of already know that. We need it to get p hat. And then the other thing is that with 99% confidence, we got to use a different critical value. And the one that we got to use is 2.576, right? That's what we figured out before. It's in that table a couple of pages ago. And then if we're going to get our 99% confidence interval, then we'd have p hat plus or minus critical value times the square root of p hat times 1 minus p hat over n. So then we're going to have 0.22 plus or minus 2.576 times the square root of 0.22 times 0.78 over 200. And then if you simplify the whole margin of error, using the ANS function and taking square roots and all that sort of thing, you end up with 0.0755 here. So then what you'll get would be the interval from 0.1455 to 0.2955. Or I think if you round this to 3 places, which is actually going to be a little more conventional here, you'd have 0.22 plus or minus 0.075, which would then give you the interval from 145 to 295. and there's the interval, right? So let's see how we would do this if we were going to do it in StatCrunch. I guess the numbers that we need are 44, 200, and 99%, right? So just remember that, 44, 200, 99%. All right, so let's get this out of here. We'll make a new one. So we go to Stat, Proportion Stats, one sample. Oops, didn't mean to click on that. One sample with summary. And then it was 44 out of 200. And then we want a confidence interval, a 99% confidence interval, so you got to change the confidence level, and then compute. Yeah, there we go, right? So to 4 places, we're in the exact same place we were, 1445, 2955. Or to 3 places, 145 and 295. So there you go. And look, it'll compute the standard error for you if you really want it, which that's the root. So like where it gives you the standard error of 0.029291637, if I go back here, it's this. It's, right, so I guess I can diagram this thing. So right here, that is your standard error. So it'll tell you what that root simplifies to if you really want it, right? That's what the SE is right here. So if you want that, you can have it, but I don't think you need that by itself very often. Usually it's just you need the lower limit and the upper limit and you're good to go. Okay, next, back into a little more theory. So what does it mean when we say we have 95% confidence or any other confidence level, 99, 90? But what does it mean when we say we have 95% confidence that the interval contains the population proportion? Well, our uncertainty really is, well, do we have one of the 95% of all possible samples that capture the parameter, or do we have one of the other 5% that don't? And we're not going to know, right? Because we don't know what the parameter is, so there's no way to check, right? But different samples are going to have different sample proportions, which would mean, right, because they're going to be different individuals in different samples, so there's going to be some variability from one sample to another, so it's not going to be the same proportion every time. So if different samples have different sample proportions, then different samples are going to give you different confidence intervals, right? So I guess in a theory sense, like these 2 points right here are a big deal. This is the hard part right here. Specifically, it's these 3. Like I think just as a concept, this is the hard part because it feels like the parameter is the variable because it's the thing that you don't know, right? Like that's how algebra works, right? The thing that you don't know is the variable, right? When you have to solve x squared minus 8x plus 7 equals 0, x is your variable, right? And you don't know what it is yet. Here, the parameter is not the variable really. It's more like an unknown constant, because it doesn't change. It, like if you're thinking about it, and this is also part of it too, you have to kind of think about the population as being at a fixed point in time. Because if you're at a fixed point in time, then the population is static, right? Like no individuals go in or out. And if the population is static, then any population measure, including like a population mean or population proportion, that's static too, right? That doesn't change. So it's effectively more like an unknown constant. But because the statistic is random, well, if you think if we're going to have a random sample, then anything that's a measure from that sample is also random, right? So I guess in a logic sense, it would be a transitive property, right? I guess that's the word that I want there. But then if the statistic is random, the interval's based on the statistic, so that's random too. Whew, lots of stuff there. That's why I said this was the hard part. If this is a thing that you can wrap your head around, which, I mean, saying it in more words doesn't really help. It's just, it's one of those things where you just have to kind of think about it for a few minutes and then you kind of go, oh, okay, now I get it. But it's not terribly intuitive. So it does take a little bit of just like kind of sitting there thinking about it. But then, yeah, 95% of all 95% confidence intervals are going to capture the parameter and so forth. So what you would get, like if you think of each of these as basically being results from a sample, where the dots are sample proportions and then the vertical lines, like the line segments are the confidence intervals. So like the ends of the line segments would be the endpoints. And if the gray line in the middle, if that's the parameter, right? So then if you think like that thing right there, if that's P, and so then our confidence intervals, so we want to see like, well, do they capture P? Sometimes they do, but sometimes they miss, right? Because this one misses, right? It doesn't get all the way down to where it crosses over that gray line. So that's what this is supposed to mean. If the red line segment crosses over the gray line, then that's a confidence interval capturing the parameter. So the first one's good, but that one misses. All these in here are good. That one's not, right? That one misses because what's happening here? The sample proportion is so low, right? Because there's the p hat right there, right? So there's p hat. It's so low that when you make the interval doesn't stretch high enough to where it would capture P, right? It doesn't get all the way up to the gray line. And the same thing happens down here with that one and that one, right? Those also miss. Because in both of those cases, the same thing's happening. Sample proportion so low that the interval can't reach high enough to capture the parameter. I guess this one up here is the opposite, right? That one, that second one from the left, where there the sample proportion so high that the interval doesn't reach all the way back down. All right, so the main thing is, usually what you have is going to capture the parameter, but you're never going to know that for sure, and sometimes they miss. And you can do everything right and still have them miss, right? You can get a perfect random sample, but you just get one that's a little weird, a little offbeat. You end up with a p hat that's kind of big or kind of small, and the interval misses. And you're never going to know, right? You're never going to know for sure. So it's just, it comes with the territory, right? It's an occupational hazard, if you want to think about it like that. I think that's a reasonable phrase to use here. You can't get rid of that issue. It's always going to be there. And you can say, well, then what if you just, ramp up the confidence level, right? Because with 99% confidence, you're going to capture the parameter more often. That's true. But if you increase the level of confidence, you're trading off with precision. Because the higher your confidence level is, the wider the intervals have to be. So wider intervals basically equate to being less precise. So there's a trade-off there. And usually 95% is kind of the happy medium, right? It's a nice high confidence level, and usually you don't get some ridiculously wide interval that doesn't really help you, right? Like if you were trying to estimate a proportion and your interval went from 22% to 48%, you're like, well, that doesn't really narrow it down that much, right? Like I would like that to be a lot thinner. And those are the kind of things you get if you pick some ridiculously high confidence level. Like if you wanted to be 99.9% confident, you can have that. Your interval is going to be really wide though, and it probably won't really give you ultimately what you're looking for, right? It won't give you the greatest estimate because it's so wide. All right, so how to interpret a confidence interval. I go deeper into this than the homework does, but if what I've gotten here makes sense, the ones that show up in the homework, you'll be able to blow through them. So nothing wrong with that. So what do you want to say? This is the kind of phrasing that you would want something like 95% confident. The things you don't want to say is you don't want to have probability words. So you don't want to say 95% probability or probability of 0.95 or 95% chance, because chance is a probability word. And it's on the next page as to why you don't want to do that. But basically it's because probability goes with variables. That's where probability makes sense, right? And when we talked about probability in chapter 5 and chapter 6, it went along with random variables. But the parameter is not a variable. That's why you don't want to use probability words. Okay, so what do you got to get in the interpretation? Confidence level, right? You want to know what kind of confidence interval you got. Is it 95%? Is it 99%? We got to get that in there. The interval itself, I guess that's the obvious one, right? If you're going to do an interpretation of the interval, what the interval is does matter, which, I mean, you would certainly think so. And then this is the tough part, the parameter. That's most of the work, writing out the thing that you're trying to estimate. Because that's what the parameter is, right? It is the thing that you are trying to estimate here. So the type of number, what that means is that's just like, is it a proportion? Or is it a mean? Or what is it? I mean, you can estimate other things, but we're just going to do proportions and means. Then whatever your population is, so like US adults or something, and then the specification or the context. So if we look here, so there's the 95% confident, and this is usually the easiest way to write it out. If you're going to write out the whole thing from scratch, put the confidence level at the beginning, right? So here's that. Right, so there's the confidence level. I probably don't need to label that. I'm sure that's really obvious that that's what that is, but I'm just going to label all the pieces. Then here are the endpoints down here. And then basically the rest of this, so I'm going to put this in green brackets. All the stuff that's in green, that is the parameter. I don't know why it's not letting me write anymore. Parameter. Okay, so there's the type of number, and I guess I gotta use a different color. I'm annotating everything here. So, right, there's the type of number. It's a proportion. So that's A, I guess. So I'll just do it like an A in parentheses maybe. And then all adults in the US, that's the population. So then that's B. And then the proportion of all adults in the US who do what? Well, who wear formal business attire to work most days. So the wear formal business attire to work most days, that would be the specification or context part. So yeah, a lot going on there, right? But the easiest thing to do is get the confidence level at the beginning, endpoints at the end. So basically 95% confident that P is between 0.066 and 0.114. And I think that's what they look like in the homework. I think basically they just don't write the parameters out, because the parameter is the thing that makes this long, right? So type of number, the proportion, all adults in the US is the population, and then wearing formal business attire to work is our context, right? You got to get all that in there just to get the parameter. But I think the ones in the homework basically just don't write the parameters out. And then there's another one in here, right? So then here, once again, the parameter is most of the writing. And notice it's the same stuff. The type of number is the proportion. All that airline's passengers is the population. And then having only carry-on luggage is the context. But then, just like before, we got confidence level at the beginning, endpoints at the end, right? So there are the endpoints, and then the confidence level right up there. All right. And in the homework, it would probably say we can be 99% confident that P is between 0.145 and 0.295. All right, then this I kind of brought up already. Why don't you want to use probability words? So this is a big trap. Like, this is the thing that you don't want. So no. And the reason that that's a no is because probability relates to random variables. And we said that the parameter is something that's fixed. It's not a variable. So if it's not a variable, like, probability ideas don't really apply to it. So the parameter is fixed. It's an unknown constant, not a variable. So I guess the easiest thing is just say 95% confident. Don't say 95% chance, and don't say probability of 0.95. And then another easy mistake to make would be including the sample instead of the population. So basically just writing out the statistic in words instead of writing out the parameter. And usually that's a one-word difference. So instead of having all licensed drivers in the US, the thing that would be trouble would be saying the proportion of licensed drivers who were surveyed who are uninsured. That's the statistic, right? That's 12.6% written out in words. So just watch for that. Make sure it applies to the population, not the sample. But the parameter being estimated, right, it should relate to all licensed drivers in the US, right? That's our population. All right. Well, then, with another example, just to get another interpretation in here. So I really push this, writing this out. But then, once again, parameter is long, right? That's it. The proportion of all adults nationwide who never pay attention to the nutritional info printed on food packages, right? So the population there is all adults nationwide because that's how it's phrased up here, right? Because then there's our sample, right? So then from there you'd say the population must be all adults nationwide. And same type of individuals, but just all of them instead of a little group. But I mean, if you look at this, it's the exact same format as the other two, right? 95% confident that parameter is between 0.125 and 0.155. What about this last part? Would it make sense to conclude that less than 15% of adults nationwide never pay attention to the nutritional information printed on food packages? So in other words, basically what this is asking, and I should do this in a different color than blue. Brown. If I take the context out, this is basically asking, is it reasonable to conclude that P, the population proportion, is less than 0.15, right? If I take all the context out, this is what that question is asking. And the reason is no. The reason for that is because in order to say that, you want the entire interval to be less than 0.15, and it's not, because the upper endpoint is 0.155. So the answer to this is no, since part of the confidence interval, and I'm just going to abbreviate confidence interval as CI, part of the confidence interval is above 0.15, right? Because it goes up to 0.155. That's a bigger number. If it was less than 20%, you could say yes, right? Because then the whole thing's less than 0.2, we're good to go. But you got to look at the whole interval, not just the point estimate. So that is the big thing there. So to answer these correctly, that's what I would say, because these come up. So I would say use interval, not point estimate. Right? So just use the whole interval. That's the important thing there. Okay. Next, I kind of brought this up already, the trade-off between having a high confidence level and having a precise interval. So if one goes up, the other one goes down pretty much. Like you could have a 100% confidence interval, but for a proportion, it would be from 0 to 1. And that's not informative at all, right? Like that doesn't tell you anything. It's like, well, yeah, every proportion is between 0 and 1. That doesn't help me. And you could also, like, if you wanted a really precise interval, you could have one. But that means that your confidence level might have to be really low. Like you might have to go down to like 80% or 60%. And then you go like, well, is that worth it if you're 60% confident? That seems kind of low compared to like 95, right? And it's usually considered not to be worth it. But fortunately, we can typically get both. Like we can get a happy medium. And usually it's 95% with a decent sample size. And if you look at most opinion polls, they're 95% confidence intervals where the sample size is around 1,000. And that's a sample size that will give you a nice small margin of error, but it's also not one that's overly huge where it would take forever to collect the data, right? So I guess socially, that's kind of what we've decided, like as a society, that's a nice happy medium there, right? 95% confidence and roughly 1,000 for the sample size. But then now, and I think this is the last big thing in this section, computing a desired sample size. So let's say we know what confidence level we want for our interval, like, we're going to have a 95% confidence interval. But we also want a level of precision to where our interval is going to estimate p to within 0.02 or something. Right? We don't want the interval to get any wider than that. That's a thing you can do. So given a target bound, so what that means, like when you're given a target bound, so it'd be something like, I'm going to put this in quotes, but within 0.02, that would be a target bound. Or within 0.04, or within 0.01, or something like that. So that gives you a bound on the width of the interval, which is the margin of error, right? That's the thing that dictates the width, because it's the part that's after the plus minus. So solving for n, you get this formula right here. However, then you think, well, if we don't have the sample size yet, then we haven't taken the sample, so how do we have a sample proportion? We don't. We got to put a value in there, and we don't have the sample proportion yet. There are two options. So this one is if you have no idea, right? So no idea about what p might be, right? No ballpark estimate whatsoever. The reason that works, if you use a 0.5 there, that maxes out the p hat times q hat. It's sort of like if you have, and this is a big thing, like when you first start doing word problems in Calc 1, this comes up. But I think even like without Calc 1, this is a thing that I think most people already know. If you have, like, let's say like you have a certain amount of fencing and you're going to make like a rectangular shape and you want to enclose the most area, the thing to do is make a square, right? That's what's going to do it. That'll give you the maximum area. And effectively, this is that concept. It's making the square. Because if p hat is 0.5, then so is q hat, which is 1 minus p hat, right? I tend to write it as 1 minus p hat, but our book uses the q hat. But that's half dozen of one, six of the other. Same exact thing. But if they're both 0.5, then that's going to max out that product. And so that way it's impossible to have a target sample size that's too small, which makes sense. If you have no idea what you're shooting for, it's okay if you end up with one that's too big. That'll actually give you something more precise than what you were asking for. Nothing wrong with that. The problem would be if you got something that's not precise enough. And the way that could happen is if your sample size is too small. So if you set p hat equal to 0.5, that makes the sample size being too small an impossible situation. So that's why you do it, just to rule out that bad thing that could happen. But if you do have an idea, use it, right? So no idea, I guess this one would be some idea, right? If we have some knowledge, and that's like if you have a similar study and you can go, well, we did the same thing 2 years ago and we don't think very much has changed since then, so we think the point estimate ought to be about the same. We're just going to use that one. Then that ends up being a reasonable thing. That'll give you a sample size that doesn't need to be quite as big. And then this is sort of a weird idea. Always round up to the next integer. And that feels sort of unconventional when the thing after the decimal point is like a 1 or a 2. But the reason that you have to do that is because if you round down, you're going to get a margin of error that's slightly too big. So that's why you have to always round up. All right, so then what are we doing here with this example? So it says a student in public administration wants to estimate the proportion of cities with private garbage collectors. They want their estimate to be within 0.05. So there's our bound, right? There's our specified bound right there. So the within 0.05, that means that our bound on the margin of error, so E in the formula, should be 0.05. And then with 90% confidence, so 90% confidence will give us our critical value. So that will mean that our Z star, or if you want to use the notation of the book, it would be Z with a subscripted 0.05, because it would be the leftover, which is 0.1 divided by 2. Either way, that's 1.645, so we need that piece. And then how many cities are going to have to be sampled? Okay, And if we look at our formula, I think I need to scroll up slightly to get it on the screen. There it is. So we have the critical value, we have E, we don't have a value for p hat, and there's nothing that we can work with here, right? So there's no previous study, there's no anything else, right? The only numbers are the bound and the margin of error and the confidence level. We got nothing else to work with. So there's no estimate for p. So since there's no estimate for p, we have no idea what to expect here. We're going to set p hat equal to 0.5. And then we should be able to do it from there. Right? So what we're going to end up with if we substitute in, we'd have that n would be equal to 1.645, since that was our critical value, over the bound of the margin of error, which is 0.05. And this thing's going to be squared. And then p hat, we said it was going to be a 0.5, but then 1 minus p hat is just going to be another 0.5. And what you'll get if you multiply this all the way out, and so I guess you probably want a calculator for this one, but what you'll get is 270.6025. But then remember, you got to round up to the next integer, so you got to round up to 271, and 271 is your answer. Okay, so the big thing here is that there was nothing for p hat. And it's easy to get stuck there, to kind of forget about what you're supposed to do there, but it's just, that's when you set it equal to 0.5 to max out that product at the end of the formula, which now would be a 0.5 times another 0.5. But we had the bound on the margin of error, the within 0.05, and then we had the confidence level, which gives us the critical value. And then we can take it from there, and then I guess just don't forget to round up at the end. All right, another example, and you know what's going to happen. This is one where we're going to have the previous study. All right, so South Dakota, believed to be the state where the largest proportion of the workforce has 2 or more jobs. And based on a survey from a few years ago, 95% confidence interval for the proportion of all members of the South Dakota workforce with 2 or more jobs was this. Okay, well usually you just get the endpoints. Why did I write out the whole thing? So that would make it easier to find the point estimate. Because the way that we've been doing this before, there's our point estimate, right? It's before the plus minus. So then that means that what we know from that interval over there to the left of where I'm writing is that p hat must be 0.097. So, okay, good. And then notice what we've got here. These are going to be important things in a minute. We want an interval estimate with 95% confidence, but margin of error no larger than 0.02. We're going to need that piece as well. All right, so first thing is, what are we going to use for p hat? Well, we kind of already went through it, but in the previous study, what we had was that p hat is 0.097. So use that, right? We've got that extra information this time, so use it, right? That's what it's there for. So we're going to go ahead and use it this time. We're going to have a 0.097 instead of a 0.5. All right. So what we're going to do here, I guess otherwise, the 95% confidence, that'll give us a critical value of 1.96. And that's one that you're going to end up memorizing whether you want to or not. So either z with a subscripted 0.025 or z star, depending on what notation you want to use. It's 1.96 for 95% confidence. And the other thing is that our bound on the margin of error is 0.02 because it says so in that thing that's circled in red, right? No larger than 0.02. Okay, great. Then if we're going to compute the desired sample size, it'll be 1.96, our critical value, divided by the bound on the margin of error, the 0.02, square that fraction, then times p hat, which is 0.097. 1 minus 0.097 is 903. And then if we simplify this, again, probably want a calculator for this part, It's 841.224 to 3 places. But don't forget we got to round up. And this is one that feels weird because there's a 2 right after the decimal point. It feels really weird to round this one up, but you got to. So round up to 842, and 842 is the answer. All right. So with the desired sample size, it's actually easier to do this with a calculator than with StatCrunch. Believe it or not, that is true. You can try it with StatCrunch if you want to, but it's tougher. And then the other thing, because this does show up in this section, I think there might be one problem where these are useful. If you have the 2 endpoints of the confidence interval, you could solve for the point estimate and the margin of error. Because when you get the confidence interval, like when you're going forwards instead of backwards, when you add and subtract the same thing, right? Because it's p hat plus or minus the margin of error, right? Margin of error is just one quantity. So if you knew what the 2 endpoints were, p hat would have to be the midpoint of your interval. So if it's the midpoint of the interval, you could just average the 2 endpoints and that would give you the midpoint. So it would give you the p hat back. So if all you had was just, I don't know, 0.164 to 0.248, let's say, then you could figure the midpoint out, right? You just add those together, you divide by 2, and then that would give you the sample proportion back out, right? So then, like for this one, I guess I have the space for it, kind of. P hat would be 0.164 plus 0.248 over 2. Whatever that is, let's see. I should be able to do this. Let's see, that's 412. So that should be 206. Okay. And then for the margin of error, well, the width of the interval is 2 margin of errors, right? Because it would go from p hat minus the margin of error up to p hat plus the margin of error. So it's 2 margin of errors wide. So if you were going to get it, you could do it this way as the difference between the endpoints divided by 2. If you already had p hat, you could also use that and say, well, it's the difference between 206 and 164, or 248 and 206. So it should be 0.042, right? So if we were going to do it for that up there, you'd have that E is, so 248 minus 164 over 2. So the difference is 0.084 over 2, which is 0.042, which we said that's what it should be, and that's working out. So, all right, if you do need those, which I think that comes up once in the homework for this section, you can get them. So if you have the endpoints, you could back solve for p hat and the margin of error.